We want to discuss the problem in homework in chapter 4, section 2, problem number 2. So feel free to pause the video in the middle because it's a problem that's relatively long. The question was given f of x, which looks like that, and they want you to find out which function, if you were to take the Maclaurin series, because x was subtracted, nothing was subtracted from x, so it's centered at 0, so it must be Maclaurin series of some function. So which function the corresponding Maclaurin series would look like this? Well, you are supposed to be quite familiar with several Taylor or Maclaurin series of functions. They are on the slides number 23. So you want to get yourself reasonably familiar with the Taylor-Maclaurin series table. So just by doing the quick comparison, you realize it doesn't really look identical to any Maclaurin series that has been provided in the sheet. However, if I do not have those coefficients n and n plus 1, then the series is going to look a lot like 1 over 1 minus x. So this is a Maclaurin series. They kind of look similar to each other, except I don't like those coefficients. So how do we get rid of the coefficient in front of each term such that I can find my original function whose Maclaurin series look like this? Well, there are two ways that we've discussed in class later in that chapter about identifying Maclaurin, getting rid of coefficients. So for example, if you have a power term which looks like this, where you have a coefficient n plus 1, then by taking the antiderivative, you have a 1 over n plus 1 popping up. So those two cancel out. You end up with x to the n plus 1. So by taking antiderivative, it can help you get rid of the coefficient n plus 1 for the term x to the power of n. Along the same line of thinking, we also discussed derivative calculation. So if your coefficient were something like 1 over n, and for the term x to the n, by taking derivative, you could do a cancellation, so you get rid of the coefficient. Therefore, if your coefficient were on the denominator, right, then by taking derivative, you can cancel the coefficient, the number that's the same as the power of your function. So let's go back to what we want to cancel. We want to cancel something on the numerator, so I want to do antiderivative calculation. I wanted to cancel n and n plus 1, one at a time, and think about it. Which one do I cancel first? Every time I take, clearly I want to take antiderivative because my coefficient are on the numerator. So every time I take antiderivative, I bump up my coefficient by 1. So I'm going to go from n to n plus 1. So I'm going to be capable of canceling with a larger coefficient later. So I'm going to cancel the smaller one first. So let's go ahead and try to get started. So we want to get rid of the n first and try to get rid of n plus 1 later. But in order to get rid of the coefficient of n, I need n minus 1 here, right? Because the coefficient I can cancel with antiderivative. It's supposed to be one number greater than my power. So when I try to cancel the coefficient n, I need to pair it with the term x to the n minus 1. So what I did here is I look at my problem. I want to make sure it's n minus 1 here. So I rewrite my function. I downgrade my power by 1 because I can factor out a term. So my original function, f of x, is factoring out x multiply whatever was left. So identical structure, except it's n minus 1 here. So let's focus on my new function, which is this, which is my g of x. If I know what's g of x times x, I get my final answer. So what's my g of x? Well, I don't know what's g of x, but I do know the antiderivative of g of x is easy to calculate. Antiderivative summation could be left out. N is independent of x, so I could pull a coefficient out. So I can do antiderivative of n times x to the n minus 1. And just like what we said, it's going to end up with x to the n because there's a 1 over n popping up, so they can be cancelled. So this is what I end up with, and the antiderivative of g of x. So it's nice, right? You see, we get rid of one coefficient in front of my structure. So all I need to do is to get rid of the other one, and then I'm all set. So what I'm trying to deal with here, I'm trying to deal with this. I want to know exactly what's that. But to make my notation easier to write, I write this whole thing, I call it h of x. So h of x is what I just calculated here. And in order to remove the coefficient, I need to do antiderivative again. So I take antiderivative of what I just found, namely h of x. What I end up with is antiderivative of literally everything I just wrote here, right? So let's do my antiderivative calculation. So I have a summation of everything, and I take antiderivative of what's left, which is n plus 1 and x to the n. So the antiderivative of this, like what we did earlier, if you do antiderivative calculation, it's x to the power of n plus 1. The c, if you were to take antiderivative, it's cx. It's indefinite integration, so there's an extra constant. So this is what I have as antiderivative of h of x. But my life is so good, right? This is what? This is literally something I'm looking forward to. I was talking about without any coefficient, just pure x to the n terms together, add together. It's 1 over 1 minus x. That's my golden bar out there. That's something I want to match to. So look at what I have. I have this term, which doesn't really look identical to what I had. I did x to the power of n. So what I did is I factor out a x. So it's x times x to the power of n, and everything is just copy paste. And this is also not exactly what I wanted. The formulation, the Maclaurin series of 1 over 1 minus x started from 0. So what do? I start from 0, and I get rid of the term which start from 0. Therefore, I'm actually going to start from 1. So what I have here is the same as that. They are the same thing because this one starts from 0, but it get rid of the term when n is 0, and the previous one start from 1. So this term is 1 over 1 minus x according to Maclaurin series. X to the 0 is 1. So I can carry out my calculation, which means the antiderivative of g of x is no longer in the power series structure. It is x times 1 minus x plus cx plus d. So having the antiderivative of h of x is not super helpful. What I want is what's f. So let's think through it. I need to know f of x. According to the definition, I need to know what's g of x. Because once I multiply x, I'm all set. But in order to know what's g of x, I don't really know that. I do understand h of x is the antiderivative of gx. So if I know h of x, I just take derivative, I can get g of x. What I know right now is what's the antiderivative of h of x. So if I know the antiderivative of h of x, I can reconstruct h of x by taking derivative. So that's my line of thinking. I was going forward in this direction to make my function look simpler and simpler. But in order to reconstruct my question, I go backwards. So first of all, antiderivative of h of x, I take derivative of this term so I can find h of x. So I find my h of x by taking derivative of what I just wrote. And you can pause the video, do the calculation, you end up with this. So I get h of x. In order to go back from h of x to gx, you look at your definition, right? H of x is antiderivative of g, so take derivative here, you end up with g. So I take derivative of my h of x to reconstruct g. You can take the derivative of this function. I'm pretty sure you can do the calculation very easily. So that's what I end up with. Once you constructed g, you are very, very close. G times x is f, which was your final question. So all you need to do is to have your g times x, you end up with your final answer. So my final answer to this problem is supposed to be that. In other words, what I'm trying to tell you is the Maclaurin series of the problem, which is summation n goes from 1 to infinity, n times n plus 1. X to the power of n actually is equivalent to that. The calculation is slightly tedious, but the idea is relatively straightforward. Basically, you you have been given a power series, it doesn't look identical to any Maclaurin series that's existing out there. So you try to do some modification. What you realize is you want to get rid of extra coefficient on the numerator, so you do antiderivative calculation. We could have done something similar by taking derivative if the extra coefficient were on the numerator. Once you get your new function, try to write it back into the function instead of keeping it as a power series. Then you reconstruct your original function. If you had taken antiderivative earlier, you take derivative to go back. If you took derivative earlier, you take antiderivative to go back. So this is a very nice and handy technique that you want to master. Well, this one is slightly further. You need to do the technique twice, but this is a very good practice.